Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show CFD analysis of an evacuated solar collector, and it will be utilized for a specific purpose, and the output of this one, that is hot air, will be utilized for a specific purpose for drying potato chips or banana chips. Actually, for this application we need to have a temperature approximately 70 degrees centigrade. The temperature is not that much of issue because we can optimize the temperature collected in the receiver. In this analysis, we'll try to get the analysis of this exhaust gas from this solar collector, and that exhaust gas will be utilized for drying the potato chips or banana chips. And we know that for drying purpose of potato and banana chips, we need temperature in the range of 70 degrees centigrade approximately. But that is not an issue. That temperature can be obtained by optimizing the exhaust temperature from this collector. Today, through this video, we'll explain the analysis part only, and the optimization part will be done in a different video. Okay, so let us start our analysis. This is the model. Model has already been made using SolidWorks software. For understanding the model, let us cut this one from specific planes. Let us cut it from front plane, and let us see the collector or the chamber where the potato chips will be dried. You can see from here, this is the pipe. Pipe will be coming from this. If we drag it a little bit, it will see the pipe will be entering at the bottom of this chamber, and we are having two chambers here. Let us drag this on this side for understanding a better way. So we are having two chambers. This is the first chamber, this is the second chamber, and at these two different chambers we will put the chips, and inside this one we will maintain a temperature of near about 70 degrees centigrade, which will be utilized for drying these potato chips or any other chips, right? Now let us see the construction details of the heat pipe. Actually, this will be done using heat pipes. It is a solar collector, and solar collectors may be of different types. Like it may be evacuated type, or it may be like extended surfaces will be there to absorb heat from the sun rays. In this analysis, we are using evacuated solar collector, and that will be utilized to increase the temperature of hot air inside this collector. Let us cut these pipes for understanding its geometry better way. We'll cut this one from different planes. Let us cut it from top plane and view this. You can see the pipes. Like at this way, you can see inside these pipes we are having copper tubes. U-shaped copper tube is provided inside these evacuated pipes. Very little amount of fluid will be there at a pressure of 0.4 bar. Okay, again we can drag it in a better way. You can see this construction. Here this location, copper tube is closed. That means it will be evacuated from bottom to up to this position. And you know that these heat pipes are actually having three different types of sections. The bottom part, which is in the form of U-shaped, this one is actually known as adiabatic section. Inside this one we are having two sections. Let us drag it and see. From here to the top section we are having two sections. This part is known as evaporator, and this part is known as condenser. Generally, the evaporator will be having more temperature compared to the condenser. Okay, and let us drag it towards the collector. Here, the end of these heat pipes, that means you can see the evaporator and the condenser are inserted inside this collector, and it is evacuated up to this selection, and the whole part of this condenser and evaporator, it is inside this collector. So there is very less amount of heat loss because all the evaporator and the condenser part is inside this collector. From here to here it is actually single part. Okay, so let us start our simulation. And you can see here, these are the plate. We're inserting the plates inside this chamber from this location, and here we have to apply two boundary conditions, that is atmospheric pressure will be there at these two locations. Now for starting this one, we have to start with flow simulation environment, and the flow simulation environment will be created with the wizard itself. Let us start from wizard, and we're starting the project number as a default project number 4 because we have already done these different types of projects. Next to that, we have to select the unit systems. Let us select SI systems, and we'll consider pressure and stress with the unit of bar, and let us select temperature to be degrees Celsius. Next to that, we are having physical features, and definitely it will be an internal analysis. It will be heat conduction in solids. By the same time, we have to consider radiation, and it will be solar radiation. Let us consider the temperature to be 40 degrees centigrade. It is hot here at Delhi, so we are considering temperature to be 40 degrees centigrade. As it is a solar radiation, we have to select this solar radiation part, and environmental temperature is 40 degrees centigrade. We can generate the solar radiation from different options. Let us select the location and time. From here, we'll select location as New Delhi, and the solar radiation actually we will consider as a default one. As a specific date, it will be time we are considering 12, and the direction of sun radiation we can see it will be Y. That can be checked from the geometry itself. The direction of solar radiation will be Y. It will be along this direction. Next to that, the gases, we'll consider air, only the input gas. Next to that, we have to select the default materials. Default material will be copper. Excluding that, we are having different other materials that will be provided during application of boundary conditions. Initially, we'll take copper as the default material, which one will be utilized for heat pipe metals, and it will be copper. Next to that, default outer wall thermal conditions. We'll consider all these things non-radiative and apply radiation effects while applying actual boundary conditions. You can see this one as non-radiating surfaces. And surface roughness we are not considering, it will be taken as default parameter. Next to that, thermodynamic parameters, we will take atmospheric pressure should be 1.01 bar, and temperature will be 40 degrees centigrade. And definitely solid parameters will also be 40 degrees centigrade. Let us finish this, and you can see that computational domain is ready. This is the computational domain. So all the model is inside that computational domain. Let us hide this domain. Let us make the model completely transparent. For viewing the dynamics of flow particles, the model is now transparent. Now we can apply appropriate boundary conditions and other initial conditions also. So we have to go back to the analysis part. For providing that computational domain, let us have a segmented view of this model. Let us cut it from specific section. You can cut it from here and provide that fluid subdomains. Insert fluid subdomain. It will be air at 40 degrees centigrade. It will be passing from this location. So we can see this is the domain for air at 40 degrees centigrade, and the adiabatic section is inside this evacuated tube. Green check. Next to that, we have to select different materials. Let us select copper materials as the heat pipe main content. Let us select copper material first. Insert solid material, predefined. It will be metals, and from metals we select copper. Let us select that heat pipes. We can select it from the geometry itself. Solid bodies, and we can select or segregate those copper pipes from the geometry itself. Here we can see these are the things, right? So initially these things are actually evaporator and condensers. We'll select one by one all these evaporators and condensers. Let us select all the evaporators and condensers separately, and you have to provide material for this one as copper. We have made the heat pipe in such way that it is consisting of three different parts: evaporator, condenser and adiabatic section. So selected, it is made up of copper. Selected. Next to that, you have to provide glass material for these evacuated tubes. We'll select solid materials again, insert solid material, predefined. It will be glasses and minerals, and from that we have to select glass. Let us select that this one as the glass materials. You can again select from the geometry itself. Glass material is selected. You can put the name of this one as glass. Done. Next to that, we have to provide solid materials. Insert solid material. It will be made up of iron. It is made up of GI pipes, these things. Predefined. It will be metals and it will be iron. We can select these things. Green check, it is done. This one we have to rename it. It is made up of iron. Again, we have to select that chamber. Let us make the container to be made up of aluminum. It will be aluminum 6061. Selected, and we can provide the name to be aluminum. Done. So materials provided. Now from radiating surfaces, we have to select the black body radiations and absorptive surfaces to be selected. Radiative surfaces, insert radiative surface, predefined. First of all, we'll select absorbent wall. The evacuated tubes will be considered as absorbent wall. Green check. Next to that, we have to select that heat pipes as black body. Radiative surfaces, insert radiative surface, predefined. We have to select black body walls. Complete heat pipe should be considered as black body walls, and that can be selected from the geometry itself. We can select the solid bodies. All the heat pipe is selected, and the property of the heat pipe is considered as black body walls. Green check. That is done. Next, to provide some other things, that means we have to provide heat pipes. For selection of this heat pipe, let us make a segmented view of this model, because we have to select the heat pipe in three different sections. You can cut it from a specific plane. Let us cut that model from some specific plane. You can cut it from top plane, in which you can select that condenser and evaporator separately again. Now let us select that heat pipe. Initially, you have to select all the components of the heat pipe, so that can be done from the geometry itself. Select. So complete heat pipe is selected. Next part, we have to select that hot part, that means evaporator part, to be selected. For selecting this evaporator part, we can make the model a little bigger. This part is actually evaporator. We can select the evaporator separately. This is the first evaporator part. Second, alternately we can select, because first one is evaporator and second one is condenser. For each tube, we have to select separate evaporators. You can see we have selected all the parts. Next to that, you have to select that condenser part. You can select it from here directly. This is the first condenser. This is the second one. This is the third condenser part. Fourth condenser part. Fifth one. Sixth one. Seventh one. Eighth one. Ninth one. And this is the last one. So next to that, you have to provide the effective thermal resistance. It is very, very less. We have seen that temperature difference for this evaporator and the condenser is very, very less. It is approximately 1 degree centigrade. And the maximum temperature of this evaporator is near about 220 degrees centigrade. So the effective thermal resistance is very, very less. Here it is. It will be 0.0025. You can check. So we have selected the heat pipe. Next to that, we can provide some boundary conditions. And boundary conditions, that means we want to provide atmospheric pressure at the exit of this chamber. And also mass flow rate of air at 40 degrees centigrade should be provided from this entry location. And also for providing boundary conditions, let us take a segmented view of this model in which we can provide boundary conditions in a better way. Let us cut it from specific location. Yes, it is done. First boundary condition, it will be air from the inlet location at a specific velocity. Let us provide a velocity of 3 meters per second from the entry location. Let us select that entry location from here. From this entry location, air will be passing at a rate of 3 meters per second. You can check. Next to that, you have to provide atmospheric condition at the entry of this chamber. You can cut it again for better selection of that location. You can cut it along specific plane. Let us cut it from front end and you can reverse the direction. Go and check. Next to that, we have to apply boundary conditions at these two locations. Boundary conditions, insert boundary condition, it will be atmospheric pressure at these two locations. So we can select these locations here, selected environmental pressure, and again you can select at this location also. Environmental pressure at the true entry location. Selected, you can check. Now you can see the complete model. This is the complete model. Boundary conditions defined completely. Next to that, we have to select some goals, specific goals. We want to have temperature at evaporator and condenser sections. By the same time, we want to have temperature at the two plates. For that one, again, let us cut the model from specific plane. You can cut the model from right plane and move towards the specific location for this evaporator and condenser. We need to find the temperature at the evaporators and condensers separately. So we'll select the goals from here. Goals, insert surface goals. We want to find the average temperature of fluid at the evaporators and condensers separately. Initially, we'll select the temperature of the evaporators. So we'll select the first tubes. We have selected. We can have a goal for each of the surfaces separately, but we don't want. That means we want to have the temperature of all the evaporated surfaces as an average temperature. It will be a single goal. You can check. So one goal is defined and we can rename this one as temperature of fluid at evaporator. Next one, we have to find the temperature at the condenser part. So it will be again another surface goal will be there. Insert surface goal. We have to select temperature of fluid at the condenser surface. We can select separately. We have selected all the surfaces for this condenser and we want to have a single goal. We are not creating separate goal for each of them. We want to select average temperature of fluid, grain check, and we can rename this one as average temperature of fluid at condenser. Done. Next one, we want to find temperature at the two plates where the chips will be provided. We can select it from here also, or better we can have another segmented view to select that location of the chips. So we can cut this model from top plane. This is done from top plane. Now we can select that specific location for the trays where the chips will be kept. So goals, insert surface goals, and in this case we want to have separate goals for two different plates. It will be average temperature of fluid at the surface of the tray, and we want to create separate goals for each of them. Grain check, and we will rename this average temperature of fluid at tray 1, and second one will be average temperature of fluid at tray 2. Done. Goals are defined. Next to that, we have to run this and get the results. We have already simulated, so it will save some time. We can see the results from project 2. It was done with the same data. Now we can see the results from project 2. Let us load the results. It is loading. It will take some time for getting the results to be loaded. We are not bothered about that, like cut plots and other things. Mainly our task is to see the temperature at the trays, different trays, right? And actually the temperature needed at the two surfaces should be approximate in the range of 70 degrees centigrade. So whatever temperature is coming, that is not the issue. We can change the temperature by varying different input variables. That can be done using optimization, and we'll do the optimization case in a different video. Now from the results, first of all, see temperature of fluid at different cut plots. Also we'll see cut plots, insert cut plot, we want to see temperature of fluid, not pressure, from different planes, right? So we can select different planes from here also. We can select from top planes and also right plane also. Let us view this one from right plane. We are selecting the right plane for viewing the different cut plots. Grain check. It can be understood in a better way. If we see this in the form of an animation, it will be understood in a better way. So we want to see these cut plots in the form of an animation. Let us play these things. You can see bottom part temperature is very high, and as it is approaching towards top part, its temperature is reducing. Again, you can see clearly inside this collector or chamber, temperature is not that much high, and the temperature at the bottom part of this heat pipe is very high, and as it is approaching towards the end, its temperature is reducing. Next to that, we want to see temperature distribution from different plane. So we'll close this part, clear and hide, and we want to see these cut plots from different plane. Let us see this one from front plane. Cut plots, insert, and we want to see from front plane. Let us see that. It is clearly understood from here that bottom part, its temperature is very high. It is in the range of 1857 degrees centigrade. It's very high at the bottom part, and as it is approaching towards the end, its temperature is reducing. Right? You can vary the temperature. Suppose we want to see the temperature from 220 degrees centigrade to 40 degrees centigrade, suppose. So here we are having mixed color, that is temperature is in the range of 190 degrees centigrade approximately in the collector at this location, and here at the surface of this tray, temperature is in the mixed zone. The temperature is in the range of 60 degrees centigrade at the tray location, that is understood by the color code of this simulated results. Right? Okay. We can see these things in the form of animation also. Let us view these things in the form of an animation. Cut plot 2, let's play. So inside this collector, at this cylindrical portion, temperature is in the range of 190 degrees centigrade, and inside this collector or the tray, the temperature is in the range of 60 degrees centigrade. That can be optimized by changing the different parameters or input variables. Right? Cut plot 2, clear and hide. Next to that, we want to see surface plots. We want to see the temperature at different surfaces of this solar collector. Insert. We'll see all the faces of this solar collector, and temperature fluid is needed, that to be checked. Green check. Surface plot is being generated. It is done. You can see throughout the plate, the temperature is in the range of 220 degrees centigrade. Actually, it's clearly visible, and inside this first collector, the temperature is in the range of 180 to 90 degrees centigrade, and inside this big chamber where the chips are kept, the temperature is near about 40 to 58 degrees centigrade, and down this portion where the chips are kept, the temperature is in the range of 60 degrees centigrade. Throughout this pipe also, temperature is in the range of 140 to 160 degrees centigrade approximately. So as it is approaching towards this big collector or this receiver where the chips are kept, the temperature is reducing because of high volume of this container where huge amount of air is kept, and the temperature of air, which was at 40 degrees centigrade, that is being increased from 40 to 60 degrees centigrade. Surface plots will clear and hide this part. Next to that, we want to see dynamics of flow particles. Flow trajectories. Insert flow trajectories, and the numbers to be 12, and instead of pipes, we want to see the dynamics of flow particles in the form of arrows only, and the diameters will be 0.01. Let us select any specific surface from where the particles will be flowing. Let us select from top surface here. We can select from any surface. Select other, and face of the revolve number 1. We're selecting face 1, green check. It will show the dynamics of flow particles from that location only. It can be viewed through the heat pipes also. So particle study is being generated. It will take some time for generating this particle study. Let us wait for some time for getting the particle studies to be generated. Particle study is generated. Now we can see it's better to see in the form of an animation. It will show how the particles are moving from this location to that big chamber. Temperature fluid we want to see in the form of an animation, right? So flow trajectories, let us play. It is showing the dynamics of flow particles, the movement of particles through this intermediate collector to the final collector. It is showing, and the color code of these different particles showing temperature at different regions. Inside this intermediate collector, the temperature is in the range of 190 degrees centigrade, and inside this big chamber, the temperature is mixed zone, At the bottom surface, temperature is in the range of 60 degrees centigrade, and at the top surface, temperature is little bit less. Okay. Next to that, we'll see the results from the gold plots. That is our main aim. So we have already seen that results from the different cut plots and the dynamics of flow particles. Next to that, we want to see the temperature distribution at different locations as per goal plots. Flow trajectories. Let us clear and hide these things. Clear and hide. Next to that, we want to see the goal plots. Insert goal plots. We want to see all the goals in the form of graphs only. So we'll transfer all these things in the form of graphs. We can export this one to Excel also. Let us export this to Excel, then we can view these results in a better way. We have 5 different goals. That means temperature of fluid at the condenser part, evaporator part, and also at the intermediate collector. By the same time, we have selected temperature at the 2 trays also, right? So the Excel file is being generated. We can analyze these things right now. This is a summary available. Now we'll see the results after that. That means temperature of fluid at the first tray is 55 degrees centigrade, and at the second tray it is 58.9, that is approximately 60 degrees centigrade. And temperature of fluid at the condenser part is 221.9 degrees centigrade, and at the receiver it is 191, and at the evaporator is 222 degrees centigrade. So the temperature difference between the evaporator and the condenser is approximately, you can say, near about 0.3 degrees centigrade, right? Okay, next to that, we want to see the results from the graphs. This one is showing average temperature of fluid at the evaporator part. After 520 numbers of iterations, the final temperature at the evaporator is 222.26 degrees centigrade. Initially, it started with 40 degrees centigrade, and after 520 numbers of iterations, its final temperature is 222.26 degrees centigrade. Next one we'll see is average temperature of fluid at the receiver, that means intermediate collector. It is approximately 191.44 degrees centigrade. Next one we'll see the temperature at the condenser. Again, here it is after 520 numbers of iterations, it is 222.01 degrees centigrade. That is, you can see the temperature difference between the evaporator and condenser is very less. It is in the range of 0.25 to 0.3 degrees centigrade. Next one, we'll see the temperature at the trays. We are having 2 trays. This is the temperature of fluid. Our tray number 2, it is in the range of 58.9. It is approximately 59 degrees centigrade. And for the second one, we can see there is a temperature of fluid above tray number 1 is in the range of 55.22 degrees centigrade. So these are the things we could see from our simulation. To get the specific amount of temperature or heat at the trays, we need to optimize these input variables, and we can get the desired amount of heat at the trays. That can be done by varying the different parameters, like maybe the inclination of the heat pipe, or it may be like the diameter of these heat pipes, or it may be the length of the heat pipes can be increased to get the desired amount of heat from this solar collector. So this is all about our today's video. Instead of going for different optimization, we are stopping it here, and the optimization part will be done in a different video. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.